Good evening. Tonight, you'll discover the secrets of one of nature's most enchanting phenomena, the aurora borealis, the northern lights. You'll learn how curtains of green and purple light dance across polar skies, how ancient peoples interpreted these celestial displays, and how modern science explains the magic above us. 100 facts about the northern lights that will guide you into the most peaceful sleep. But first, if you want more journeys like this, subscribe to the channel and leave a like right now, because in just a few minutes, you'll be too relaxed to move. Now then, make yourself comfortable. Let your body sink into your bed. Close your eyes. Tonight, I invite you on a journey to the far north, to places where night skies come alive with color, where ancient peoples watched in wonder, where science and beauty meet in perfect harmony. 100 remarkable facts, told slowly, gently, without haste. Earth is approximately 4.54 billion years old. 4.54 billion years. That's 4,540,000,000 years. A number so vast, it becomes almost meaningless to our human minds. If you compressed Earth's entire history into a single year, humans would appear only in the last few minutes of December 31st. All of recorded history would fit into the final seconds before midnight. Everything we know, every civilization, every empire, just the last tick of the clock. Our planet didn't begin as a planet at all. It started as a cloud of dust and gas, orbiting a young star. Our sun, newly born, surrounded by the remnants of its formation. This was the solar nebula, a swirling disk of material spinning slowly around the infant sun. Within this disk, tiny particles began to collide, to stick together. Dust grains becoming pebbles, pebbles becoming rocks, rocks becoming boulders. Slowly, over millions of years, these objects grew, building up, piece by piece, until they became planetesimals, the building blocks of planets. About 4.5 billion years ago, something dramatic happened. A Mars-sized object, called Theia by scientists, collided with the young Earth. This wasn't a gentle collision. It was violent, catastrophic. The impact melted both bodies, vaporized rock, sent debris flying into space. But from this destruction came creation. The debris from the collision coalesced into a ring around Earth, and from that ring, the moon was born, our closest companion in space, born from chaos, now gently lighting our nights. After the moon-forming impact, Earth was unrecognizable. The surface was an ocean of molten rock, magma, glowing red and orange, stretched across the entire planet. Temperatures exceeded 1,200 degrees Celsius. There was no solid ground, no water, no atmosphere as we know it, just liquid rock, slowly cooling, releasing gases into the void above. This was the Hadean Aeon, named after Hades, the ancient Greek underworld, a fitting name for this hellish period of Earth's infancy. Slowly, over millions of years, the surface began to cool. A thin crust formed, fragile at first, breaking apart and reforming, like the skin on cooling pudding. Steam rose constantly from the surface. Water vapor, trapped in the rocks, was being released, along with carbon dioxide, nitrogen, and other gases. These gases accumulated, creating Earth's first atmosphere. Thick, dense, nothing like the air we breathe today, but it was a beginning, the first step toward a world that could support life. The young Earth was bombarded constantly. Asteroids and comets, leftover debris from the solar system's formation, crashed into the surface regularly. Some were small, Others were massive. Each impact released tremendous energy, melting rock, creating craters, adding material to our growing planet. This period is called the Late Heavy Bombardment. It lasted for hundreds of millions of years. Interestingly, many of these comets carried water, ice from the outer solar system, delivered to Earth through these cosmic collisions. Around 4 billion years ago, something remarkable occurred. The surface had cooled enough, the bombardment had lessened, and conditions became right for liquid water to exist. The first rains began to fall. Imagine that moment. After millions of years of a molten surface, the first drops of rain, hissing as they touched hot rock, evaporating instantly, but slowly, persistently, cooling the surface further. These rains continued for thousands of years, perhaps millions, rain falling, evaporating, falling again, until finally, water began to pool. The oceans formed gradually. First, small pools, then lakes, then seas, and finally, vast oceans covering much of the planet's surface. These early oceans were different from today's seas. They were acidic, hot, rich in dissolved minerals from the rocks. But they were water, liquid water, one of the essential ingredients for life. Earth had become a water world. Perhaps 90% of the surface was covered by these primitive oceans. Only scattered volcanic islands broke the endless expanse of water. The early atmosphere was toxic to us. There was almost no oxygen. Instead, carbon dioxide dominated, along with nitrogen, methane, ammonia. The sky would have appeared orange or reddish. The sun, shining through this thick atmosphere, would have looked different, dimmer perhaps. Lightning storms were common, electrical discharges crackling through the atmosphere. These storms played an important role in creating complex molecules from simple gases, the building blocks of life being assembled in the sky. Beneath those early oceans, volcanic vents spewed minerals and heat. These hydrothermal vents created zones of warmth and chemical richness, oases in the dark ocean depths. Around these vents, in the warm, mineral-rich water, something extraordinary was about to happen. The first stirrings of life, the first chemical reactions that would lead, eventually, to living organisms. But we're getting ahead of ourselves. Take a moment, breathe. Let your shoulders relax. You're doing wonderfully. We've traveled 4 billion years already, and we've barely begun. Somewhere around 3.8 to 4 billion years ago, life appeared on Earth. We don't know exactly how. We may never know. But somehow, in those warm, chemical-rich waters, simple organic molecules began to organize themselves. They formed chains, structures, eventually something that could replicate itself. The first life, not cells as we know them, but something simpler, self-replicating molecules, the ancestors of all life on Earth. These first life forms were single-celled organisms, bacteria-like, living in the oceans, feeding on chemicals from volcanic vents, reproducing by splitting in two. They had no nucleus, no complex structures, just a simple cell membrane containing genetic material and the machinery of life. Scientists call these organisms prokaryotes. They dominated Earth for billions of years. In fact, they still do. Bacteria outnumber all other life forms on our planet today. For hundreds of millions of years, these simple organisms evolved. They adapted to different environments. Some lived in hot water, others in cold. Some in acidic conditions, others in alkaline. Life was experimenting, testing what was possible, spreading into every available niche. And slowly, these organisms began to change the planet itself. This is important. Life didn't just adapt to Earth. Life shaped Earth, transformed it, made it into a different kind of world. About 3.5 billion years ago, something revolutionary happened. A group of bacteria evolved the ability to perform photosynthesis. They could capture energy from sunlight, use it to convert carbon dioxide and water into sugars, and as a byproduct, they released oxygen. These organisms were cyanobacteria, sometimes called blue-green algae. They formed large colonies in shallow water, building up layer upon layer, creating structures called stromatolites. You can still find stromatolites today in a few places around the world. Ancient forms, still growing, much as they did billions of years ago. At first, the oxygen produced by cyanobacteria didn't accumulate in the atmosphere. It reacted immediately with iron dissolved in the oceans. The iron oxidized, rusted, and sank to the ocean floor. This process created vast deposits of iron ore, banded iron formations, layers of red and black rock, stripes of oxidized and unoxidized iron. These formations, found around the world, are evidence of that ancient oxygen production. They're also economically important. Much of the iron ore we mine today came from this process billions of years ago. For over 1 billion years, cyanobacteria continued their work, slowly, steadily, producing oxygen, transforming the chemistry of the oceans, and eventually, around 2.4 billion years ago, something remarkable happened. The iron in the oceans was exhausted. There was nothing left to react with the oxygen, so the oxygen began to accumulate in the atmosphere. This is called the Great Oxidation Event, one of the most important moments in Earth's history. The rise of oxygen was actually catastrophic for most life at the time. Oxygen is reactive, corrosive. For organisms adapted to an oxygen-free world, it was poison. Many species went extinct, unable to survive in this new oxygenated environment. But for other organisms, oxygen opened up new possibilities. It could be used for respiration, a far more efficient way of extracting energy from food. Organisms that could use oxygen thrived. Life adapted, as it always does, and the planet continued to change. Around 2 billion years ago, another major innovation occurred. A larger cell engulfed a smaller bacterium, but instead of digesting it, the two began to cooperate. The smaller bacterium specialized in producing energy using oxygen. It became a mitochondrion, the powerhouse of the cell. This symbiotic relationship created eukaryotic cells, cells with a nucleus, with specialized compartments, with much greater complexity. These are the cells that make up plants, animals, fungi, everything we see around us. For the next billion years or so, life remained single-celled, but these single cells were becoming more complex, developing new capabilities, new structures. Some evolved the ability to capture light using chloroplasts. They became the ancestors of plants. Others became specialized predators, hunting and consuming other cells. The microbial world was diversifying, becoming more sophisticated, setting the stage for the next great transformation. Around 800 to 600 million years ago, something extraordinary happened. Single cells began to stick together, to cooperate, to specialize. Some cells became responsible for gathering food, others for reproduction, others for structure and support. This was the beginning of multicellular life, the first simple animals and plants. At first, these were tiny, microscopic, simple sheets or filaments of cells. but they represented a profound shift from individuals to communities, from simple to complex. If you're still with me, wonderful. If your eyelids are growing heavy, that's perfect too. Let yourself drift. Let these words wash over you like waves on an ancient shore. About 541 million years ago, life exploded in diversity. This period is called the Cambrian, and the sudden appearance of many new life forms is called the Cambrian explosion. In a relatively short period, geologically speaking, perhaps 20 to 25 million years, most major animal groups appeared. Creatures with shells, with jointed legs, with eyes, with complex body plans. The oceans teemed with strange and wonderful forms, many unlike anything alive today. One of the most famous Cambrian creatures was Anomalocaris, a predator, perhaps a meter long, with grasping appendages near its mouth and compound eyes. It was one of the largest animals of its time, swimming through Cambrian seas, hunting smaller creatures. Its name means abnormal shrimp. Though it wasn't a shrimp at all, it belonged to an extinct group, related to arthropods perhaps, but unique. The Cambrian seas were dominated by trilobites. These arthropods, distant relatives of modern insects and crustaceans, came in thousands of species. Some were tiny, others the size of a dinner plate. Some crawled on the sea floor, others swam in open water. Trilobites had compound eyes, segmented bodies, hard exoskeletons that fossilized beautifully. They would go on to dominate Earth's oceans for the next 270 million years, before finally going extinct. During the Cambrian, the first chordates appeared. Chordates are animals with a notochord, a flexible rod running along the back, the precursor to a backbone. One early chordate was Pikaia, a small, worm-like creature, swimming through Cambrian seas. It doesn't look like much, but Pikaia, or creatures like it, were our ancestors, the beginning of the line that would lead to fish, to amphibians, to reptiles, to mammals, to us. Throughout the Cambrian, life was still confined to the oceans. The land was barren, lifeless, just bare rock and sand, shaped by wind and water. There was no soil. Soil is created by the action of plants and bacteria breaking down rock. Without life on land, there could be no soil. The landscape would have been alien to our eyes, beautiful in its starkness, but empty, silent, waiting. Around 485 million years ago, the Cambrian gave way to the Ordovician period. Life continued to diversify in the oceans. Coral reefs appeared. Cephalopods evolved, becoming some of the ocean's top predators. The first primitive fish emerged, jawless, armored, bottom feeders, but fish nonetheless. And on land, finally, the first pioneers appeared. The first organisms to colonize land were likely lichens and mosses. These hardy pioneers could survive desiccation. They could extract moisture from the air, could cling to bare rock. They began the slow process of breaking down rock, creating the first primitive soils, preparing the way for more complex plants. This was a monumental step. Land, for the first time in Earth's history, was turning green. By the Silurian period, around 440 million years ago, true vascular plants had evolved. These plants had specialized tissues for transporting water and nutrients. They could grow taller, could colonize drier environments. The first simple forests appeared, not trees as we know them, but primitive plants, perhaps waist-high, creating the first terrestrial ecosystems. With plants on land, animals soon followed. The first land animals were arthropods, millipedes, scorpions, spiders. They scuttled among the primitive plants, fed on decaying vegetation, or hunted each other. These early land animals were small, but they were pioneers, adapting to a new world, learning to breathe air, to prevent water loss, to navigate on legs rather than fins. Around 400 million years ago, during the Devonian period, fish underwent a revolution. They evolved jaws, bony skeletons, fins supported by bones rather than just rays of cartilage. Some fish developed lungs, allowing them to gulp air at the surface, useful in stagnant, oxygen-poor waters. And some developed muscular lobed fins they could use to prop themselves up, to push along the bottom, perhaps even to pull themselves onto land. These lobe-finned fish were the ancestors of all land vertebrates. Let yourself sink deeper into relaxation. Your breathing is slow, steady. You're traveling through time, effortlessly, peacefully. By the late Devonian, around 375 million years ago, the first tetrapods appeared. Tetrapods, four-legged animals, the first vertebrates to walk on land. They evolved from lobe-finned fish. Gradually, their fins became legs. Their bodies adapted to support their weight out of water. Early tetrapods still lived mostly in water, venturing onto land to hunt, to escape predators, to move between pools. But they were taking the first steps, quite literally, toward a terrestrial existence. One of these early tetrapods was Tiktaalik, discovered in Arctic Canada in 2004. It lived around 375 million years ago. Tiktaalik had fish-like features, scales, fins, gills, but also features adapted for land: a flat head, a neck, robust ribs, and fins with bones that could support weight. It could do push-ups, prop itself up on its fins, perhaps even pull itself onto muddy banks, a transition form, perfectly illustrating the evolution from fish to tetrapod. During the Carboniferous period, 359 to 299 million years ago, life on land flourished spectacularly. This was the age of forests, but not forests as we know them. Giant club mosses, tree ferns, horsetails, some growing to heights of 30 meters or more. These forests covered vast areas, creating the first extensive terrestrial ecosystems. And when these plants died, they fell into swamps, where they were buried before they could fully decay. Those buried plants, compressed over millions of years, became coal. Vast deposits of coal, found around the world. Most of the coal we use today was formed during the Carboniferous. It's preserved sunlight, energy captured by photosynthesis hundreds of millions of years ago, stored in the earth, waiting. The name Carboniferous means coal-bearing, a period when so much carbon was locked away that atmospheric CO2 levels dropped significantly. The Carboniferous forests were filled with arthropods, giant arthropods, dragonflies with wingspans of 70 centimeters, millipedes 2 meters long, scorpions the size of small dogs. Why so large? The atmosphere contained more oxygen than today, perhaps 35% compared to 21% now. Higher oxygen levels allowed insects to grow larger. Their breathing system, which relies on passive diffusion, could support greater body size. These creatures would have been spectacular to see, but perhaps a bit unsettling too. The first reptiles appeared during the Carboniferous. They evolved from amphibians, but with a crucial innovation: the amniotic egg. This egg had a shell and internal membranes that protected the developing embryo and provided it with nutrients. This meant reptiles didn't need to return to water to breed. They were fully adapted to land life. This innovation would prove crucial. It allowed vertebrates to colonize even dry environments, to spread across the continents. Around 299 million years ago, the Carboniferous gave way to the Permian period. The supercontinent Pangaea was forming. All the Earth's land masses drifting together, colliding, creating mountain ranges, forming one gigantic continent. This changed climates. The interior of Pangaea was far from any ocean. It became arid, desert-like, but life adapted. Reptiles diversified. Some became specialized herbivores. Others became fierce predators. One group of reptiles, the therapsids, evolved features that made them look surprisingly mammal-like. They had differentiated teeth, specialized for cutting or grinding. They may have been warm-blooded. Some perhaps even had whiskers or fur. These were the ancestors of mammals, though mammals themselves wouldn't appear for millions of years yet. Therapsids dominated terrestrial ecosystems during the Permian. They were the ruling class of life on land, around 252 million years ago. The Permian period ended, and with it came the greatest mass extinction in Earth's history. Over 90% of marine species went extinct, 70% of terrestrial vertebrate species. It was a near-total reset of life on Earth. The causes were complex. Massive volcanic eruptions in Siberia, climate change, ocean acidification, a cascade of environmental changes. But I won't dwell on the extinction itself. Instead, let's focus on what came after. Life, remarkably, recovered. It always does. Given time, given opportunity, new species evolved to fill empty ecological niches. Survivors diversified, adapted, spread. The Triassic period, which followed the Permian, saw the rise of new dynasties, including the dinosaurs. Take a moment. Notice how relaxed you are, your muscles loose, you're breathing deep and slow. You're safe, comfortable, drifting through ancient times. Dinosaurs appeared around 230 million years ago. At first, they were small, modest, just one of many groups of reptiles. But they had certain advantages: an upright stance, legs positioned directly beneath the body. This made them efficient walkers and runners. Over time, dinosaurs grew in diversity and size, eventually becoming the dominant land animals for over 160 million years. The Triassic period, when dinosaurs first appeared, was warm and dry. Pangaea still existed as one supercontinent. The interior was desert, but along the coasts, life thrived. Early dinosaurs shared the world with many other reptiles, including the ancestors of crocodiles and the ancestors of mammals. Small, shrew-like creatures living in the shadows. By the Jurassic period, around 201 million years ago, dinosaurs had diversified tremendously. Massive sauropods, long-necked herbivores like Brachiosaurus and Diplodocus, some exceeding 30 meters in length, weighing as much as 80 tons. These were the largest land animals ever to walk the earth, moving through forests of conifers and ferns, consuming enormous quantities of vegetation. Not all dinosaurs were giants. Some were small, swift, intelligent for reptiles. Compsognathus, about the size of a chicken, darting through undergrowth, hunting insects and small prey. And many dinosaurs, we now know, were covered in feathers, not for flight initially, but for insulation, for display, for thermoregulation. Dinosaurs were not the slow, lumbering reptiles once imagined. Many were active, dynamic, complex. During the Jurassic, the first birds appeared. They evolved from small feathered dinosaurs, theropods, carnivorous dinosaurs that walked on two legs. Archaeopteryx, one of the earliest known birds, lived about 150 million years ago. It had feathers and wings, but also teeth, claws on its wings, a long bony tail, a transitional form, part dinosaur, part bird, beautifully illustrating evolution in action. While dinosaurs ruled the land, other reptiles dominated the seas. Ichthyosaurs, dolphin-like marine reptiles, streamlined, fast swimmers, hunting fish and squid. Plesiosaurs, with long necks or large heads, four paddle-like flippers, gliding through Mesozoic seas. And mosasaurs, enormous marine lizards, some exceeding 15 meters in length, apex predators of the late Cretaceous oceans. The skies too were filled with reptiles, pterosaurs, flying reptiles, not dinosaur, but their cousins. They ranged from sparrow size to truly enormous. Quetzalcoatlus had a wingspan of 10 to 11 meters, as wide as a small airplane. These creatures soared over Mesozoic landscapes, fishing in rivers and seas, hunting small animals, masters of the air. During the Cretaceous period, from 145 to 66 million years ago, flowering plants appeared, angiosperms, plants that produce flowers and fruit. This was revolutionary. Flowers attracted insects for pollination, more efficient than wind pollination. Fruits encouraged animals to disperse seeds. The relationship between plants and animals became more intricate, coevolution, each shaping the other. As flowering plants spread, they transformed landscapes. Grasslands appeared, deciduous forests, plants with broad leaves. These new plants provided new food sources, new habitats. Herbivores adapted to eat them. Predators adapted to hunt those herbivores. By the end of the Cretaceous, the world looked surprisingly modern in some ways, though of course, dinosaurs still roamed. 66 million years ago, the age of dinosaurs came to an end. An asteroid, roughly 10 kilometers in diameter, struck Earth, near what is now the Yucatan Peninsula in Mexico. The impact was catastrophic, but I won't describe the immediate effects. They're too dramatic for this peaceful journey. Instead, let's focus on what came after, on recovery, on renewal. You're halfway through our journey. Your body is deeply relaxed. Your mind is calm. Let these words carry you gently forward. There is no universal now in the universe. Because of relativity, simultaneity is relative. What you perceive as now here on Earth is different from now on a distant planet. Time depends on your frame of reference. The present moment isn't universal. It's local, personal, bound to your particular point in space-time. In a way, we each inhabit our own, slightly different present. Time zones were invented for railroads. Before the 1800s, every town kept its own local time, based on the sun. Noon was when the sun was highest, which varied by longitude, but trains needed coordination, schedules, so time zones were created, standardized, an agreement about what time it is. Time became less natural, more convenient, more artificial. The international date line is completely arbitrary. It runs mostly through the Pacific Ocean. When you cross it, you jump forward or backward a day, instantly, by convention. There's nothing physical there, no actual boundary in space, just an agreement, a line on a map, and yet, it defines yesterday and tomorrow. Time is surprisingly invented by us, for us. Astronauts on the International Space Station age slightly slower. They're moving at high speed, and they're in a weaker gravitational field. Both effects make time pass slightly more slowly for them, After 6 months in space, an astronaut is about 0.007 seconds younger than they would have been on Earth. A tiny difference, imperceptible, but real, measurable. Time flows differently up there. A day on Earth is getting longer, very slowly, about 1.7 milliseconds per century, because the moon's gravity is gradually slowing Earth's rotation. Billions of years ago, a day was only about 6 hours long. In the distant future, it might be 50 hours or longer. Time, even the day itself, is not constant. It evolves, changes, drifts. Nothing is truly permanent. Humans have an internal circadian rhythm, about 24 hours, give or take, even without external cues. Your body knows roughly when to sleep, when to wake, when to eat. This rhythm is maintained by a group of cells in your brain, the suprachiasmatic nucleus, your master clock. Right now, your clock is saying it's time to rest, time to let go, time to sleep. Jet lag happens when your internal clock doesn't match external time. You fly across time zones. Your body thinks it's noon, but the sun says it's midnight. The mismatch creates fatigue, confusion, disorientation. It takes about a day per time zone for your clock to adjust, your body recalibrating, finding its rhythm again. Time inside you needs to sync with time outside you. Some people are naturally morning larks, others are night owls. Genetics plays a role, your chronotype. Some people's circadian rhythms run slightly shorter. They naturally wake early, feel energetic in the morning. Others run longer. They stay up late, feel best at night. Neither is better, just different internal timings. You have your own rhythm, your own relationship with time, and that's beautiful. Seasonal affective disorder is related to light and time. In winter, days are shorter, less sunlight. For some people, this disrupts their circadian rhythm, affects their mood, their energy. Light doesn't just let us see, it regulates our internal time, tells our bodies what season it is, what time of day, how to feel. We're connected to the sun's rhythm, to Earth's spin, to the cosmos. Your body temperature follows a daily rhythm. It's lowest in the early morning, around 4 or 5 a.m., and highest in the late afternoon, around 5 or 6 p.m. Humans have been creating time capsules for centuries, messages to the future, objects preserved, buried or sealed, waiting to be discovered by people who haven't been born yet. It's a hopeful act, an assumption that there will be a future, that someone will care, will remember. Time capsules are gifts across time, from one now to another now, years away. The oldest message in a bottle was found 132 years after it was sent, cast into the sea in 1886, found on a beach in Australia in 2018. The bottle had drifted, waited, survived storms and currents for over a century. Inside, a note about a German ship's voyage, simple information, but also a voice from the past, reaching forward, saying, "I was here, I existed." DNA can store information for millions of years. Scientists have successfully stored data, books, images, encoded in synthetic DNA. And that DNA, if properly preserved, could last longer than any hard drive, any paper, any stone tablet. Perhaps one day, messages will be sent across time, written in the language of life itself. The Svalbard Global Seed Vault stores seeds for the future. Deep in the Arctic, in permafrost, millions of seeds from around the world, preserved, protected, a gift to future generations. In case of catastrophe, in case of need, these seeds wait, patient, timeless, Life, preserved across time. Hope, frozen but alive. Photographs freeze time, a moment captured, forever unchanged, while everything around it ages, moves on, changes. The photograph stays the same. It's beautiful and a little sad. We can look at who we were, but we can never return there. Time moves in only one direction, but the memories remain, preserved in images, in stories, in hearts. Human cells have internal clocks called telomeres. At the end of each chromosome, there are protective caps, telomeres. Every time a cell divides, these caps get a little shorter. Eventually, they're too short, and the cell stops dividing, ages, dies. It's a biological clock, counting down from birth. Time is written into our very cells. The oldest confirmed human lived to be 122 years old. Jeanne Calment, born in 1875, died in 1997. She met Vincent van Gogh, lived through 2 world wars, through the invention of cars, planes, computers. 122 years, more than a century of time, of experiences, of memories, an incredibly long life, and yet still finite, still bound by time's flow. Some organisms don't seem to age at all. The Teratopsis dohrnii jellyfish can revert to its juvenile form, effectively resetting its biological clock. It might be biologically immortal. Hydras also show negligible aging. They could potentially live forever, if not killed by predators or disease. Time affects different organisms differently. For some, it might not be a limit at all. Humans age at different rates. Some people look young at 60, others look old at 40. Genetics, lifestyle, environment, stress, all play roles. Chronological age and biological age aren't always the same. 2 people born on the same day might have bodies that are years apart. In aging, time passes, but we experience it uniquely. The concept of retirement is less than 150 years old. For most of human history, geologists measure time in eons, eras, periods, and epochs. The Earth's history is divided into vast stretches: the Hadean Eon, the Archean, the Proterozoic, the Phanerozoic, each one representing hundreds of millions of years. We're currently in the Phanerozoic Eon, the Cenozoic era, the Quaternary period, the Holocene epoch, though some say we've entered a new epoch, the Anthropocene, the age of humans. Time, at geological scales, is almost incomprehensible. The Grand Canyon reveals nearly 2 billion years of Earth's history, layer upon layer of rock, each one formed at a different time. The Colorado River has carved through them, exposing a cross-section of time itself. You can walk down into the canyon, and with each step, travel millions of years into the past, touching rocks that were formed before animals existed on land. Stone is time made visible. Fossils are time travelers, the remains of organisms preserved in rock. Some are just thousands of years old, others hundreds of millions. Trilobites, dinosaurs, ancient ferns. They show us what life was like in times we can never visit. They're proof that time was real, that the past actually happened. Each fossil is a message from deep time, saying, we were here, we lived, we existed. The Earth has experienced 5 major mass extinctions, times when most life on the planet died: the Ordovician, the Devonian, the Permian, the Triassic, the Cretaceous. Each one reset the clock. In a sense, life rebuilt, evolved new forms, filled new niches. Time continued. Life persisted. We're living in the aftermath of the last one, 66 million years ago, when the dinosaurs vanished, when mammals had their chance. Ice ages come and go in cycles. For the past 2.5 million years, Earth has oscillated between cold periods with vast ice sheets and warmer interglacial periods, like now. These cycles take tens of thousands of years, driven by changes in Earth's orbit, wobbles in its spin, tilt in its axis. Time, at this scale, creates climates, shapes continents, builds and melts glaciers. We're living in a warm moment between ice ages. Imagine that. Your entire life, every human civilization, every city and culture, all occurring in one brief interglacial period, a warm pause in the rhythm of ice. The hourglass was invented around the 8th century, sand flowing through a narrow opening from one glass bulb to another, a simple, elegant way to measure time. Unlike water clocks, hourglasses weren't affected by temperature. They could work anywhere, on ships, in cold climates, reliably, the sand falling grain by grain, each one a tiny moment, together, making hours. Pocket watches became popular in the 16th century. Time became portable, personal. You could carry it with you, check it whenever you wanted. No longer did you need to find a church tower or wait for a bell to chime. Time became individual, each person with their own timepiece, their own awareness of the hour. Wristwatches were initially considered feminine. Men carried pocket watches, but during World War I, soldiers needed their hands free. They needed to check the time quickly, in the trenches, so they strapped pocket watches to their wrists. And after the war, this became fashionable, practical. Now, wristwatches are universal. Fashion changes how we relate to time. The first quartz watch was made in 1969. Quartz crystals vibrate at a precise frequency when electricity passes through them. This made watches far more accurate than mechanical movements. The quartz revolution. Suddenly, affordable watches could keep better time than expensive mechanical ones. Time became democratized, precise. Salvador Dali painted melting clocks, the persistence of memory. Clocks draped over tree branches, soft, liquid, dreamlike. He wanted to show that time is not rigid, not mechanical, but fluid, subjective, malleable. In dreams, time doesn't follow rules. Hours pass in seconds, or seconds stretch into eternity. Dali captured that strange relationship we have with time. Ancient Greek philosophers debated the nature of time. Heraclitus said everything flows. You cannot step in the same river twice, because the river changes, you change. Time is constant change, constant motion. Parmenides disagreed. He said change is an illusion, that being is eternal, unchanging, that time is not real, just a trick of perception. These debates continue today. What is time? Is it real? Or is it something we invented? The Buddhist concept of impermanence centers on time. Nothing lasts. Everything changes. Every moment is birth and death, arising and passing. The only constant is change itself. This isn't meant to be depressing. It's meant to be liberating. If nothing lasts, then suffering doesn't last. Pain doesn't last. This difficult moment will pass, and beautiful moments are precious precisely because they're temporary. Time teaches us to appreciate what's here now. T.S. Eliot wrote, "Time present and time past are both perhaps present in time future." Poetry tries to capture time's mystery, how memories live in the present, how the future is shaped by now, how it all interpenetrates, blends, becomes something more complex than linear progression. We carry our past, we imagine our future, and both exist right now, in this moment, in your mind. Music exists entirely in time. A painting, you can look at all at once. A sculpture, you can walk around. But music must unfold. Note after note, measure after measure. It only exists in its passing. You can't experience a symphony all at once. You must surrender to time. Let it carry you through the composition, from beginning to end. Music is time made audible. And in a way, this recording you're listening to is the same. It unfolds, carries you through 100 facts, from beginning to end, a journey through time and about time. H.G. Wells popularized the concept of time travel in 1895. The time machine. A scientist builds a device, travels to the distant future, sees humanity evolved or devolved into strange new forms. Wells understood that time is a dimension, that theoretically you might travel through it, just as you travel through space. The idea captured imaginations and has never let go. Einstein's theories suggest time travel to the future is possible. Move fast enough, or spend time near a massive gravitational field, and when you return, less time will have passed for you, more for everyone else. You will have traveled to their future. This isn't science fiction. It's proven physics. Astronauts do it. Very slightly, but measurably. Time travel to the future is real. Time travel to the past is more problematic. It creates paradoxes. The grandfather paradox. If you go back and prevent your grandfather from meeting your grandmother, then you're never born. But if you're never born, you can't go back. So he does meet her, so you are born. So you do go back, and on and on. Some physicists think the universe would prevent such paradoxes. Others think parallel timelines might form, each decision creating a branch, a new timeline. We don't know. We may never know. The past remains locked, accessible only through memory, through records, through imagination. Tachyons, if they exist, would travel backward in time. Hypothetical particles, faster than light. Today, over 8 billion humans live on Earth. We inhabit every continent except Antarctica. We've adapted to deserts, mountains, islands, polar regions. Our species, Homo sapiens, has become the most widespread large animal on the planet. Modern humans have transformed Earth's surface significantly. About 40% of ice-free land is used for agriculture, croplands, pastures, orchards. Cities cover a smaller percentage, but their influence extends far beyond their boundaries. Roads, dams, quarries, the visible marks of human activity. We've also transported species around the world, deliberately and accidentally, crops, livestock, pets, but also weeds, pests, diseases, ecosystems that were isolated for millions of years, now contain species from other continents. This is creating novel ecosystems, new combinations of species, interacting in ways never before possible. The ocean continues to be vital to Earth's climate and life. It absorbs carbon dioxide from the atmosphere, produces oxygen through photosynthetic algae, regulates temperature. The ocean is not a single thing. It's a complex system of currents, layers, ecosystems, from sunlit surface waters to the mysterious depths, where strange creatures live in eternal darkness. Earth's forests remain incredibly important. Tropical rainforests, temperate forests, boreal forests in the far north. They produce oxygen, store carbon, create habitats for countless species. regulate local climates. A single large tree can be home to thousands of organisms, insects, birds, fungi, lichens, mosses. Forests are not collections of trees, they're communities, interconnected, interdependent. Soil, humble soil, is one of Earth's most complex substances. A handful of healthy soil contains billions of bacteria, fungi, nematodes, arthropods. These organisms break down organic matter, cycle nutrients, create the conditions for plants to grow. It takes centuries to form. It can be lost in a single generation. It's the foundation of terrestrial life. The water cycle continues. As it has for billions of years, water evaporates from oceans, forms clouds, falls as rain or snow, flows in rivers back to the sea. This cycle is driven by the sun's energy. It distributes heat around the planet, shapes weather, sculpts landscapes. The water you drink was once in a cloud, in a river, in the ocean, in the body of a dinosaur perhaps. Water cycles through Earth's systems, ancient, eternal, ever-changing. Earth continues to be geologically active. Plates still move, slowly, millimeters per year, but relentlessly. Mountains are still being built. The Himalayas growing slightly taller each year as India pushes into Asia. Volcanoes erupt. Earthquakes reshape coastlines. Islands are born from underwater volcanic activity. Earth is alive, not in the biological sense, but dynamic, changing, never static. Life continues to evolve. Evolution hasn't stopped. Every generation, genetic variation, selection, adaptation. We see it in bacteria developing antibiotic resistance, in insects adapting to pesticides, in birds changing migration patterns. Evolution operates on different timescales. Some changes happen quickly, others take millions of years, but it continues, always. As long as there is life, there is evolution. Earth, our home, is approximately 4.54 billion years old. We've journeyed from its fiery birth through the emergence of oceans and continents, the first stirrings of life, the age of dinosaurs, the rise of mammals, and finally to the present day. Every era has been unique. Every period has seen transformation. And through it all, Earth has remained, changed, adapted, but endured. A blue jewel in the darkness of space, carrying life, carrying possibility, carrying us. We've traveled together through 4.6 billion years, from molten rock to living world, from single cells to the complexity we see around us. It's been a long journey, through unimaginable stretches of time, but we've arrived here, now, this moment. Earth's story continues. It doesn't end with us. The planet will go on, changing, evolving, long after we're gone. But for now, for this moment, we're part of that story, part of Earth's great narrative, and that's something worth dreaming about. Let these images drift through your mind. Ancient seas, forests, creatures long extinct, the slow dance of continents. Let them become part of your dreams. You are safe. You are comfortable. You are exactly where you need to be. The Earth continues its journey around the sun, as it has for billions of years, as it will for billions more. And you, resting now, are carried along, part of that ancient rhythm, part of that story. Breathe deeply, let go, drift. May these stories lull you into the deepest, most peaceful sleep. May you dream of ancient oceans, of forests older than memory, of stars wheeling overhead. May you rest well. Good night.